Okay, so basically, where were we in the end of the last lecture? We have investigated the connection between omega and k, the dispersion relation, for two cases. One was a simple one-dimensional system with equal masses and, if you want, spring constants between them. And after guessing that we have a wave solution for the equations of motions, we went through some algebra and got to a point where we can write down the dispersion relation. And what we got was where k where a is a distance here, n is a number of atoms until the periodic boundary condition, and when we plotted so the dispersion relation starts linearly and ends flat. Am I allowed to pull k for larger values? Indeed, but I'm allowed.
Yeah, you wouldn't really get any information. You can't even do measuring wise because the quantize will look the same.
Exactly. What I'll see, if I'll just naively continue to draw it, okay, no problem. And so on and so forth. Why is it meaningless?
Because you would measure it the same, like
Physically.
that's what I mean, measuring the same. If you have two, like quantized, if you only measure by quantized intervals, like discrete intervals, it would same as higher frequency, higher wave numbers will look the same as lower wave numbers, even not considering the frequency, if we map them out.
I would like to emphasize your answer to make it a bit more transparent. Basically, we remember that the symmetry of a lattice is basically right. I change my vectors, my lattice vectors, by an amount of the lattice vector, nothing happens. I see exactly the same. This translates into K, the behavior of K, as we have seen. So, yes, indeed, if I move K by G, and G here is 2 pi over A, so if I move from here to here, I will see exactly the same, because to describe what's happening in this system, all I need is the K values in the first Brillouin zone. You remember, first Brillouin zone is the behavior up to a unit cell of size G. Okay, so mathematically, I'm definitely allowed to continue with it. Physically, it's meaningless. Now I'll throw a question that I won't answer till another 4 or 5 lectures, but since we're discussing the subject, it's a good place to raise it. What happens if this wave wasn't a wave of phonons, but a wave of electrons? Okay, if I go and play with K, I remember that for a free electron, I have a wave function e to the power I k dot r divided, not divided by anything. And I have an energy which is proportional to k squared. Right? But that was for the cases where I can move my space in any amount. The plus r here doesn't change anything. I don't have a vector, I don't have a lattice, I don't have fixed discrete symmetries. There I have a continuous symmetry. I can move space by any amount and all is good. So I have an energy that behaves like k squared. If I put an electron in a lattice, I'm saying we will prove it, that the solution for the energy looks something like that. So, does it mean that electrons can't go and have higher energies in a lattice? Point for contemplation. We will answer. but it's just to whet your appetite. Basically, playing with the symmetries of space has a strong influence on the properties of particles that live in the space. If you want to let your imagination go free, if our space is continuous or discrete, it should have a fingerprint in the behavior of a free electron. Let's say, let's come up with a physics where space is discrete. You're supposed to see some signature to it somewhere. Okay, but at the moment we are with phonons, and this is the behavior that we calculate. Okay, we did another exercise in the previous lecture. This was a very similar problem. All atoms still had a mass m, but the spring constants between them fluctuated between k and g. Okay, and we solved that problem. Then we got two branches, two solutions for each value of k for the dispersion relation. And then we said, well, if I take the case I'm supposed to see the same solution. Because if I consider this lattice as 2 electrons per unit cell, or 1 electron per unit cell, it's my choice. It's like choosing a basis. It shouldn't change the physics. So, let's stop a minute and consider what changed in this problem.
Change the length of the discrete. So that means that we have a higher maximum wave. We should have a higher maximum wave number if we were to measure instead the smaller lengths.
Simply stated, now the distance between Bravais lattice points is, let's call it A2. And okay. For our solutions, we have now K2. And what is the length of the expression for K2? Well, the same as here. 2 pi divided by unit cell length, which in this case, let's write it in 2 stages. And what is N2? How many steps on my Bravais lattice do I have to perform in order to get back to the origin? That's a step length. How many steps? If previously it was n, now it's n divided by 2. Right? Because if I have n electrons and n atoms, and each unit cell is composed of 2 atoms, I have n over 2 unit cells in order to get back to the origin. So K didn't change. Since the steps in K didn't change. Okay, let's write down the solutions that we got. Okay, we got omega. In this case, we had 2 branches. All of this we did in the previous lecture. So if you need to refresh the solution, just look in the previous lecture. And here I'm not bothering to write K0, it's K. We used K0 because we didn't want to define everything G and K equal to K from the beginning. We used some separations there and only took the separation to 0 at the end. Okay, these were the 2 solutions. And if I'm looking at this solution for a moment, and replacing A2 by A, lo and behold, I got this solution. But what's going on with this solution? Have an additional solution that is different. But remember, when we started this calculation, we have here still the property it's one-dimensional, so I'm not bothering to write vector here. Okay? Okay? Basically, I'm getting this solution sign moved by the reciprocal vector of my new solution. The problem here, why I'm getting in this case two different solutions, is because I'm defining basically a different value of A and G for the new solution, and then canceling that out, but it remains in my solutions. If K wouldn't have been equal to G, then I would have two true solutions, which one of them where basically this branch is the acoustical branch, and we call it an acoustical branch for the simple reason that when K goes to zero, omega goes to zero linearly, like an acoustic wave. And here it's a constant. And once we get to the Brillouin zone boundary, there's still a gap between them, and there are two distinct solutions, branches. So this is called and the movement of the particles is different. For the acoustical branch, if I'm moving from one atom to the other, their displacement for small values of K is almost the same. It's a long wavelength solution. Why is it a long wavelength? K is close to zero. What is the wavelength? 1 over K.
Is 2 pi over K.
Right, so if K goes to zero, the wavelength is large, meaning that it's a long a wave that changes only slightly from one atom to the other, which is plotted here. If one atom moved by some amount, the atom near it moved by a similar amount. On the other hand, the optical wavelength, is the motion in the optical branch is different. Basically, we can have opposite movement in each atom. Think about it in the limit where, let's say, K is very strong compared to G. Okay? What do you expect to see? Basically, you have here a lattice of two strongly coupled masses, right? Two, and then two, and then two, and the interaction between them is very weak. Okay? So, what do I expect? Vibrations between those two strongly coupled units, and on very long scale, some movement of these two atoms. Almost completely decoupled, almost completely different behavior, which is exactly what you see here. Okay, if I had more than one or two of two atoms in a unit cell, what would I get? I would get more and more optical branches. Okay, what is the next step? Let's be generous. Let's immediately move to 3 dimensions and leave 2 dimensions for the exam. Okay, so for 3 dimensions, we wrote a very general form of the harmonic interaction, and now we'll use it. Why do I call it very general? basically, here I can stick in how many dimensions I want, right? If mu goes only to 1 and nu only to 1, we are back to our one-dimensional example. If for some reasons I'm interested in a 5-dimensional lattice, no problem. I'll take mu and u to 5. And I didn't assume necessarily nearest neighbor, because r minus r prime could be any distance that I want. When we did one dimensions, we assumed that it's nearest neighbors, like a spring constant. But basically, any forms that I want, any movement in the x direction at a point here, how is it coupled to a movement in the z direction of a point here? It's all here. Okay. Nevertheless, not everything that I can dream of can go into this D. I have some restrictions. One of the most basic restrictions is symmetry. Doesn't matter if I'm looking on this atom interacting with this atom, or this atom interacting with this atom. It should be the same. Why? Well, physically it's clear, but also mathematically. If you remember the definition of U harmonic, it was a second derivative. And of course, changing the labels R and R prime, mu and nu has to leave me with the same expression, because the order of the derivation doesn't matter.
You use this assumption in the factor of 1/2.
Right. But I'm reminding you basically
Why it's okay.
why it's okay. Another thing, Yes, but it doesn't make any difference for the conclusion.
Why do you need a half? You didn't need a half.
For the argument, you don't.
Because you have a half in there.
You pulled. Sorry, you pulled out the half here.
Oh, right.
And perhaps the most surprising what does that mean?
Basically means it can't act on itself. Like the specific particle can't self-propel a basic physical principle. General phenomenon here.
I would like to illustrate it in the following way. So I wrote it for a specific movement of all the atoms. Okay, let's assume that we're moving all the atoms in the amount that corresponds each time to a movement of one lattice space. Okay? So, because moving all the lattice just by a lattice vector doesn't change the energy, right? Think about taking a lattice and moving it in space just to a different origin of the lattice vector. Nothing changes. So, since this is not zero, this must be zero. Okay, so these are very general symmetry statements which we will use now to write equations of motions. What are we going to do now? Exactly what we did for the one-dimensional case. We'll take U harmonic, we will write equations of motion and see what we get. So I'm leaving here the harmonic part. How many such equations do I have?
As many as there are the index of U.
Well, I have for all n atoms, I'm assuming now that I'm in a regular lattice, I have one atom per unit cell, n times the number of dimensions. In 1D we had n equations. Here we have, let's say if we are doing a three-dimensional, 3 equations. So 3 times n equations. Okay. What happened to the sum over R?
But we picked a specific R.
We picked here a specific R. So the derivative leaves only one component. All the others fall out. And we have picked a particular mu. So we are left here only with a sum over nu and R prime. As we did before, we'll choose a solution. We'll check a solution. What solution will we pick? E to the I kr. And the only thing that I'll add to the game, since I'm in 3 dimensions, someone can guess? Of course, k is a vector.
Boundary condition for the
I'll take my usual periodic boundary conditions.
polarization.
Polarization. Because the amplitude of can now wiggle in different directions. I have to take that into account. If it would have been an electromagnetic wave, I would know that it's perpendicular to K, but no such thing for acoustic or or a sound wave like these phonemes are. Actually, I'll have a longitudinal and a perpendicular component. Okay, so I'm writing the solution as U of R Okay, so this is the usual wave solution that I would have written for a three-dimensional case, and I'm adding polarization. We'll see why it's important. Okay, and okay, if I go a distance n times a1 in a direction, I'm returning to the same place. But I have to take here into account, and I won't bother to write it 3 times, but you understand. That I have boundary conditions in 3 directions. For simple cubic, it will be simple perpendicular, but it doesn't have to be. It depends on the shape of the lattice. And of course, to generalize what we did in the previous one-dimensional case, K are solutions in the first Brillouin zone. Shorthand for what we did exactly in the one-dimensional case, here in the three-dimensional case. What did I do? Nothing much. I just wrote this solution. Sorry, this solution into my equation and perform a second derivative according to t. That's all I did at this point. Okay. I'm looking at it and R prime and what screams to me in this equation? Have a sum over R prime, right? It's not a simple sum, it is our beloved Fourier transform. If at the end of any solution in physics you don't end up with a Fourier transform, start worrying. So, let's define okay, regular definition of a Fourier transform. What bothers me a bit that doesn't bother me.
No, you don't care.
It's discrete, okay, that's you're working on a discrete lattice. What do you want? Your Fourier transform to be continuous?
Otherwise, how can we solve it?
It's a definition. Let's see how we solve it. But at the moment, a discrete Fourier transform of an object that is discrete, right? The only thing is that here I have R prime and then here I have R minus R prime. Okay, so add here and allowed. The minus will go into this game. R minus R prime, or because it's symmetric, it doesn't matter. And I'll have here IKR, which summation is not an R, can come before the summation. And I'm ending up with Just pulled out omega t kr before the summation. That's that. Okay, so I'm left only with solving this compact equation. Let's take another look on this Fourier transform. So explicitly I'm writing down the Fourier transform. Okay, so that's the Fourier transform as we defined. Hey, what did I do here? I added a bunch of stuff, right? Why am I allowed to do it? A constant times the sum of mu, d mu, proves that it's zero. So sum over d mu nu r, we proved 10 minutes ago that it's zero. Twice it probably is also zero. So I'm allowed to do this. I have a symmetry between r and minus r. So I can split my e to the power I kr to e to the minus I kr plus e to I kr half. So all I did here is mathematically massaging the expression.
I get the sine squared.
Is it? So So, the fact that in one dimension I had an acoustical wave is not something unique. I have it for any dimension. Because whatever the dimension is, I see that for small k's, the dispersion relation, remember that this goes into here, so this is connected with omega. Small k's here will result in small omegas. K goes to 0, omega goes to 0, an acoustical solution. So that's a general feature. Okay. We still have 3 directions here, right? Mu would be x, y, z. Okay, let's stop a minute and look on our beloved matrix d mu mu. Okay, what is the properties of this matrix?
Symmetric.
Symmetric, because exchanging mu and mu won't change anything, and it's real. Why is it real? Because it's forces at the end of the day. If it's symmetric and real, what do we know from quantum mechanics? Or actually from linear algebra, which we used a lot in quantum mechanics.
Eigenvalues.
It has eigenvalues which are real, and the number of eigenvalues is the size of the matrix, and it has eigenvectors, right? So I can diagonalize it. So basically, instead of writing d mu mu, I have a basis that is not necessarily the xyz basis. It could be any basis, depending on the properties of the lattice at the end of the day, where d is diagonal, and it has eigenvalues, eigenvectors in this basis, and not the one that it's written here. Some basis that diagonalize it. How do you find it? Well, you're experts now. So, we ended up from this equation I'm writing here S and not mu to remind myself that the directions are not necessarily the x, y, and z that I started with. I have 3 directions which depend on B. They should be orthogonal, but not necessarily x, y, and z. So it's basically the same solution that I had for a 1D system. Something times sine square of k dot r. But the directions depend on the properties of the lattice, and that I could find only by writing down the harmonic component of the interaction and diagonalizing it. But the main solution of the main conclusion of all this mathematical exercise is okay, this is the most general Ravel lattice that I can think about. You have the acoustic branches. I showed you 3, but you can do it for any dimension. And I didn't prove it, but it's a generalization of what I did in 1 dimension. P equal 1, P equal 2, we had 1 acoustical branch, 1 optical branch. This is a generalization of that conclusion. Okay. How can I measure these branches? On what do they have an influence?
Propagation of sound waves, maybe.
Is propagation of sound waves, scattering of, let's say, X-rays. We'll touch upon it. But the first and foremost influence that it has is actually on the heat capacity of the system. Right? Because I have here a mode that carries energy. According to the number of modes, that's the number of degrees of freedom that are in the game. The number of degrees of freedom can be seen by the heat capacity. Then you should stop me and say, oh, this is a terrible measure. Why? Because basically you could forget all this calculation. You see? Just count the number of atoms, multiply them by 6, divide by half, and you have the prefactor of the heat capacitance, right? So all that we did here, acoustical branches, optical branches, don't play any role in this in the calculation of the heat capacitors, right? Classically right, quantum mechanically wrong. So heat capacitance at low temperature will tell us something about how many acoustical branches do I have and how many optical branches I have. On a very, very rough conceptual level. Why? What is the huge difference between optical and acoustical waves? Okay, let's go a step. Even a step before that. Quantum mechanics, in the simplest and most naive statements that I can say about it. What is it? Energy is discrete, right. So, if I'm thinking about quantizing the energy for each mode, what is the quantization of energy?
They act like harmonic oscillators, so let's say something like each bar omega.
Right. Now, if I give it a small omega, a small frequency into the gate, the acoustical waves will be able to give or take this quanta of energy, because omega goes to 0 and k goes to 0. Yeah, it's fine. We'll get along. We'll find a way to swallow this energy quanta. Do the optical modes, branches can accept these small quantas of energy? No, they need an amount which is finite, because when k goes to 0, omega 0 is finite. So as I go up in temperature, at the beginning only the acoustical waves are in the game, and later on the optical waves come into the game. So it won't be the simple answer of heat capacitance exactly the number of electrons times 6 times half kT, because some of them can't use this small amount of energy. So measuring heat capacitance at small values of t tells us something about the different branches of the phonons. Okay, so now we're starting to treat this phonon. Until now we treated them classically. Now we'll start to treat them quantum mechanically. Okay. So you see in this course we pull out concepts from everywhere. Quantum mechanics, thermodynamics. How will I quantize these phonons?
Allow the wave numbers. We quantize them.
let's do it a step at a time. Well, I could go to the Hamiltonian. I have their particles, right? And quantize the Hamiltonian. What do I mean by quantizing the Hamiltonian? Changing P and X everywhere that they appear to an operator, right? That's the usual form of doing quantization, right? You had a free particle, you knew that it behaves like P squared over 2m. You said you want to quantize it. P acquired a hat, meaning became an operator. Then you had Schrödinger equation, you solved it. So here you have n p's, right, for the n particles. You have n x's, or x, y, z, for the n positions of the atoms. You have Hamiltonian. Enjoy. By the way, that's exactly what you'll do in the first step in field theory. That quantization is actually a bosonic field from which you will pull out properties of bosonic particles in field theory. Exactly the same Hamiltonian. That's known as field quantization. Why field? Because you have an n going to infinite number of coordinates, and you quantize them. But that you'll do in graduate school, not here. Here we'll do what was customary to do in the old quantum mechanics between 1905 and 1925. And we have our good old friends that played around in that era, mainly Einstein. And Einstein was the first one who thought about how to quantize these phonons. So to make life easy, and since it was used to photons, said, okay, omega has a dependence on k, right? Good, no problem. I know the solution of an harmonic oscillator for an omega, a specific omega. Let's sum up n independent harmonic oscillators, which I know the solution of, and just write down the quantized energy of the system. To move it because I'm at the end of the board. Which is the solution for n independent harmonic oscillators times the number of the dimensionality, because each of them can move x, y, z, or in this case I'm taking s, the direction of the diagonalization of this matrix D. Surprisingly, go through the whole mathematics of graduate school of what I described, you'll get the same. Go through all the mathematics of solving Maxwell's equation, you'll end up with the same. Those are the energies of the system. Okay. I'm looking at it, and one problem that should immediately come to mind, someone is prepared to raise it.
If the just pushed it more than one direction.
No, S, if I have one dimensional, would be 1, if 2, 2, if 3, 3, I don't care about it. Excuse me?
אוסילטורים. יש תלות בזה כש...
Oh, so one point is, why are you treating them as independent? The answer, you can always do a transformation, this diagonalization of D, which will give you independent solutions. That comes out from the mathematics that we didn't do of the full field quantization, but that's correct. Just looking at that equation, something here should bother you. Sum over n of half, what will it give you? Sum over this guy. This guy could be 0 at, let's say, high case and stop the summation. This guy goes to infinity. You have infinite energy.
You have to limit the omega.
No, but there's no reason. So if n is finite, yes, okay, you get a finite result. If n is infinite, you have a problem. That's a glimpse of one of the problems that haunt you in field theory. Every naive calculation like, what is the energy of a field? Infinite, I can go home. Nothing to calculate. So, it's all nonsense, everything is infinite here? No, because at least at this simple level, you can ask your questions of what happens in one state compared to another state. Right? How much energy I have to add to the system to go from one state to another state. That's finite. Because both states have this. And that's a very naive glimpse into the solutions that are done in field theory. You don't ask meaningful questions on the total energy, because it's meaningless. You ask what changed in the energy if I go from one state to another state. And the same here. Why I'm asking about the heat capacity? What is heat capacity? Derivative of the energy. Once I'm asking questions about the derivative of the energy, all is good, but because that doesn't matter. I'm just asking how NKS changed. So this is our starting point. Actually, you did a lot of it in statistical mechanics, but we will apply it specifically for our problem of the problem of phonons, and that we'll do in the next lecture.
Thank you very much.
אני כבר אמורה לעשות את זה, אבל היה לו קורס אחר עכשיו, אם יש לך ואתה יכול לעשות את זה, אני אשמח.